Good morning, everybody. I hope that you are all having a fantastic day, and we are going to jump into chapter 2. So, chapter 2 is all about chemistry. Now, I know that you hear that word and you cringe just a little bit because chemistry. However, chemistry is extremely important as we go into the workings of the human body. It is actually the foundation, which is why it's chapter 2. We already went over chapter 1, our intro to human anatomy and physiology, and now chapter 2, the second step of this class, is going to be about chemistry. Now let's do a quick review from chapter 1. So we talked about anatomy and physiology, and we know anatomy and physiology. We said that anatomy, another word, can be our structure of the body, specifically the structure of something. So, how it is shaped. And how it is shaped has a very close relationship to its physiology, which how it functions. We know that the structure and function are very closely related, just like anatomy and physiology, which is why that is the name of this course. And so structure actually determines the function. So I said if you know the structure and the function of a lot of different things, then you will be in good hands. Whatever we learn, you probably want to know the structure and the function of them. I did add one more shun to this list. We said if we know the structure and the function, and then another word has to deal with the terms that we learned last chapter. So all of the vocabulary words, all of the bolded terms, all of the italicized terms also tell us with their prefixes, their suffixes, and their directional terms where these things are in the body. And the where has to do with another shun called location. So if we have the structure, the function, and the location of literally anything, if you know those three important things about anything in the body, you will be set. If we know the structure of a skin cell, we know its function is to protect the body, being the outermost layer, and we know the location of it being maybe on the forearm. Then I could tell you exactly what type of cell is on the forearm. However, we have the same structure and function of the outermost layer of our skin everywhere, except if I told you that the skin cell was on the forearm versus the palm of your hand, those would be two different locations and might actually change the structure and the function because the outermost layer of skin on our hands has to do something a little bit different than the skin on our forearms. Yes, it's protecting us, but also we have a lot more tactile cells on the palms of our hands because we touch everything with our hands. You don't necessarily touch everything with your forearm to see what it is. You have a little bit less sensation on your forearm because of that. So that location is going to come in handy. So we have anatomy and physiology, the structure, function, and the location of anything in the body. So let's very quickly go over our levels of organization because in our chemistry chapter, we're going to go over the smallest levels of organization. So we said, what are our smallest levels of organization? Yep, we have our subatomic particles. Subatomic particles include what? Because we're going to go over them today. Yes, our protons, neutrons, and electrons. These are going to be the small particles that make up something. We said they are sub, so they are below. If they are smaller than, what is our second part of the word? Subatomic. So if we put all of these particles together, we are probably going to get an atom. So before we go up to that, our subatomic particles, we said protons, neutrons, and electrons. These all have a specific charge. Our protons are going to be positive, our neutrons are going to be neutral, and our electrons are going to be negative. And we'll talk about why those are very important as we continue along. So put those subatomic particles, protons, neutrons, and electrons together, and we get an atom being the building block of the world. If we put one or more atoms together, we get a molecule. If we put one or more molecules together, we get a macromolecule. Macro. Ooh, that's really not spelled right. Macromolecule. If we put those macromolecules together, we get an organelle. Remember, we are looking at the full word, not just organ, because an organelle is going to be smaller than the building block of the living things, our cell. Building block of all living things. So we have a cell. We put one or more cells, so a layer or mass of cells that have a similar function together. We get a tissue. We put one or more tissues together to serve a common function. We finally get that organ word that we're looking for. If we put one or more organs together, we get an organ system. And we put all 11 of our organ systems together, we get a human organism. So now we have finally gotten to the largest among. Remember, we need to know from smallest to largest and from largest to smallest continually. And today we are mostly going to be talking about our subatomic particles. So subatomic, probably up to a molecule, our particles. We're going to molecule, atom, and our subatomic particles there that we are going to be going over. For our chemistry. So, the importance of chemistry in anatomy and physiology. I know we said the word chemistry, and some of you don't like it. I will agree with you. When I first went through college, I was not a huge fan of chemistry. I had to retake it. I did, because I did not learn it in accordance with what I was interested in. So taking chemistry on its own sometimes is difficult. If you love chemistry, more props to you. I did not like it because I'm not a huge fan of math, and chemistry was like math but with chemicals and different letters. So that was a little bit more difficult to learn on its own. But you guys get to learn it in accordance with what we are trying to find out about the body. So that is one thing that I think is so incredibly lucky, because you get to know exactly how it relates to the body, and that means how the body is working immediately, instead of taking 12 weeks talking about Avogadro's number and exactly what polarity is. We are going to talk about what polarity is. We are going to talk about how chemicals work, but we are going to talk about them in relation to anatomy and physiology, in relation to the structure and function of the body. So, why are we studying chemistry? Chemistry is concerned with the composition of substances and how they change in chemical reactions. So we're talking about the composition of substances. We just talked about all of the levels of organization of a human organism. So starting at the bottom, we have our subatomic particles, our protons, neutrons, and electrons. And we have to know exactly how those react with other protons, neutrons, and electrons, because each of those building up an atom might have a different number of these subatomic particles. We know, looking at the periodic table, that some of them have higher protons, neutrons, and electrons, and some have lower. Because if we look at the chemical hydrogen, which is from an H, this has an atomic number of 1. This means that it has 1 electron. So we have a small nucleus and a single electron here on the outside circling it. So our hydrogen is going to have 1 electron. But if we look at oxygen, oxygen has an atomic number of 8. So we're going to have that nucleus there in the middle, and we're going to have an inner ring with 2 electrons, and then we're also going to have an outer ring with 4. Sorry, 4, 5, 6, 7, 8. 6. I told you I can't math. So 1, 2, 3, 4, 5, 6, 7, 8. Yes, so we have 6 in the outer ring and 2 in that inner ring. 2 plus 6 equals 8. Very good. So we can see that the chemical structure of this hydrogen atom is going to be very simple compared to this oxygen atom. And so this oxygen atom is going to react differently with different chemicals than this hydrogen is. And so knowing this composition of each of these chemicals has to deal with how we know they're going to react. Obviously, oxygen is very, very important in our body. We already said that the biological definition of respiration is making energy. And the way that human organisms do that is by taking in oxygen and then giving it out as a waste product. So that's going to turn oxygen, it's going to pick up some carbons, and it's going to turn into carbon dioxide. So we're going to have carbon dioxide, di being 2, so we have 2 oxygen and 1 carbon. So knowing this chemical composition of oxygen has to tell us something about the chemical composition of carbon as well, as to why oxygen is going to react with it. And we will get into that. So this also tells us how they change in chemical reactions. So if we know what oxygen looks like by itself, it has an atomic number of 8, meaning it has 8 electrons and some other numbers of protons and neutrons, which we will get to. Then we'll know that the number of electrons is why they're going to react, and how this oxygen atom is going to change when it binds to carbon to make carbon dioxide. So knowing that is going to be able to help us understand why humans use oxygen to make energy, not just in respiration, quote unquote, in our breathing, but also in delivering oxygen to different chemical reactions. Why in glycolysis we have in cellular respiration, why we have some anaerobic or aerobic reactions. Anaerobic meaning we do not have oxygen in those reactions, and aerobic meaning we do have oxygen in those reactions. So why can some reactions happen without oxygen while others require oxygen? Our understanding of exactly what this atom looks like and how it interacts with other atoms is going to give us that answer every single time, which again is why chemistry is so important to learn. Our human body, food, and medications are all composed of chemicals. If we know more about those chemicals, we know how they will react and what happens when we have too much of a certain chemical or too little of another. All anatomical structures are chemicals, and all physiological processes are based on those chemical reactions. So I just talked about how the body makes energy, respiration. So how the majority of our cells make energy is through cellular respiration. We already said the definition of respiration is making energy. So cellular respiration is how the cells make energy. And how a cell makes energy has both aerobic and anaerobic reactions. We just said all physiological processes are based on chemical reactions. So we just talked about 3 different types of chemical reactions, and our understanding of those chemicals in them is going to give us a lot better understanding of what they're actually doing. The structure of the chemicals, the function because of that structure, so whether or not hydrogen is going to bind to oxygen or if oxygen is going to bind to carbon, helps us determine via the structure and function, and then the location of that. So if we are binding oxygen to carbon dioxide to carbon in a cell versus in our lungs, is going to tell us why that reaction is occurring: structure, function, and location. And then lastly, water and electrolytes make up all of our body fluids. So water being H2O. So here we already have our hydrogen being in play and our oxygen once again. So we have a double atom. We have two atoms of hydrogen having a single electron, while we have one atom of oxygen having 8 electrons. But knowing the structure of them is going to help us understand how they are reacting. So before we move on to the fundamentals, we're going to take a quick foray into some astrophysics a little bit, just a little bit. I am by no means an expert on astrophysics, but we're going to talk about exactly how the world was created via chemicals. So we already talked about hydrogen. We know that the periodic table starts with hydrogen with a single atomic number. We know that the second chemical on the periodic table is going to be helium. This has 2. Can we look at a periodic table for what is number 3? It is going to be lithium. I'm quite sure. So we already have 1, 2, and 3 on the periodic table. Now, why are these important? We already said that hydrogen only has a single electron here. So that must mean that the atomic number also has to deal with that. So helium has 2, while lithium now has 3. So on the broad scope, I'm going to say that the most important thing about these atoms is their electrons. Their electrons are what give them the ability to react to each other. So our electrons give the atoms something called electronegativity. And if they have a higher amount of electronegativity, the more reactive they are going to be. So if we have more electrons, or a different number of electrons, they are going to want to react with each other. So back to helium. Helium is our first atom in the world. Hydrogen. Hydrogen is going to be our first atom in the world. So let's say out in space, we had a whole lot of nothing but hydrogen. So we had hydrogen atom, hydrogen atom, hydrogen atom, hydrogen atom. I'll just start putting the letter that it's associated with as the nucleus. So we have a whole bunch of hydrogen atoms. Now, what do we know about gravity? There's still gravity in space, even though there is anti-gravity, but gravity has to deal with mass. Because if we have a larger mass, then there actually is gravity. Think about the Earth. Why do we have gravity on the Earth? It's because a certain amount of mass exists on the Earth already. We have a molten core, we have a lot of rock, and so that mass is pulling us towards it, which is also why we have the moon. The moon works with gravity. It circles around the Earth because the Earth has a pull on that giant rock. So if each of these hydrogen atoms, even though they look small, have some mass, and we know they do because they have those subatomic particles: proton, neutron, and electron. So each of these hydrogen atoms are pulling, because we have more hydrogen atoms, more hydrogen atoms, more hydrogen atoms. We are going to be pulling all of these hydrogens towards the center of this. And as we get more and more hydrogen atoms, they're basically going to create a cloud of hydrogen. A full cloud of hydrogen until there is so many hydrogen atoms that we've created so much push and so much pull towards the middle that we are going to cause a fusion reaction. A fusion reaction occurs when there is enough pressure put on two atoms that is actually going to cause them to fuse together. They become one thing. So we take a hydrogen and a hydrogen and we fuse them together. So we are taking a single electron atom and a single electron atom. If we now only have a single nucleus and we 1 plus 1 electron, we now have 2 electrons. What do we have after that fusion reaction? Can we look up here? Yep, we have helium. So we have taken hydrogen and another hydrogen, and with enough gravitational pull, with enough mass in the middle, we have caused a fusion reaction that has led to the creation. We have created helium out of a hydrogen and a hydrogen. So now we have some helium in the middle of this cloud. We now have some helium. So some of these have 2 because we have put so much pressure on the middle that we've caused helium in the middle. So let's say we take even more pressure. Now we're adding more hydrogens. More hydrogens are still coming together into these clouds, but we have clouds of helium. Helium is a bigger atom. Helium is now a bigger atom, so it has a bigger mass. So now we have all of these heliums in the middle and all these hydrogens on the outside. So what if we have a helium and another hydrogen? So we have a 2 electron atom and a single electron atom. We have another fusion reaction because there is so much gravitational pull towards that center of these clouds, of these atomic clouds. And so we have a 2 atom plus, or sorry, a 2 electron atom plus a single electron atom, and we get 3 electrons. So what chemical has 3 electrons? That's right, we look up here. That is going to be lithium. So lithium has now been created. So all of these fusion reactions are happening at the center of this cloud. These are actually what are occurring on our sun. We have both fusion and fission reactions occurring over and over and over again. And that is what is creating those solar flares, because we're literally building chemicals. We are literally creating chemicals out of this gravitational push and pull, this fusing and breaking apart of chemicals because of the amount of mass that occurs there. Now we can go all the way up the periodic table from from hydrogen to helium to lithium to beryllium to all the way up until iron. So if we look at iron, iron is going to be Fe, and iron is going to be the heaviest element that can be made via a fusion reaction. So this is the last element made by fusion reactions. Because we have put all of these elements together in the middle of this cloud, all the way up until iron, we can create them naturally. Once iron is the middle, we now have a metal at the middle of this atomic cloud, of this giant mass, and we can no longer fuse iron with the next one. So then the rest of the periodic table becomes naturally occurring elements mixed with synthetically made elements. So all the way up until, I don't remember the number, but a certain a certain chemical are naturally occurring elements, but the last about 20 or so are synthetic elements, which means that they have been created in a lab. Some of them can only exist for a second or so, and even existing for a second, they have different numbers of protons, neutrons, and electrons, telling us what exactly has occurred. So back to this fusing. I said this is what's occurring in the sun. We know that the sun is a star and that all stars are basically in the future, because if you're looking at the light of a star, it has traveled millions of light years, so much distance that we are literally seeing light from the past, because those stars that we're looking at most likely no longer exist. So the first time that this occurred, there was so much fusing until it could not occur anymore, that we had a fission reaction, which is what led to the Big Bang, which means that so much happened in here. So much mass occurred until we then exploded. So it went all the way out and through all of these chemicals across the universe, the Big Bang. So through those chemicals, and those chemicals, specifically from this fission reaction, is what makes up the universe today. So you can say that you, as a human, are literally made up of the atoms that occurred during this reaction. So you, yourself, are stardust. You are literally made from stardust. That's a pretty cool thing. So this is how the Big Bang occurred, how the world started, with all of these chemicals. We can always go back to those levels of organization from the smallest subatomic particle. Our protons, neutrons, and electrons making up the atom, making up the chemical, is what is going to give us life, what is going to give us this ability to react with other chemicals. And what makes you stardust, which is very, very cool, if I do say so myself. So we talked a little bit about these things. Let's talk about the fundamentals of chemistry. So we said matter, things that have matter, is anything that takes up space and has mass. Although I want you to look at this because the definition of matter and mass are two different things. So anything that has matter does have mass. And any mass is the amount of that matter present. So mass is anything that takes up space and has basically mass, has a thing on it. We know that matter is composed of elements, solids, liquids, and gases are matter. So all of the base states of existence. Mass is the amount of that matter present. So if we have a little bit of mass, we have a little bit of matter. If we have a lot of mass, we have a lot of matter. But make sure that we have those definitions. They overlap just a little bit. And then that mass is different than weight, because mass is the amount of matter present. So think of how big something is. It has more mass if it is bigger. It has less mass if it is smaller, leading it to have more or less matter. The weight is going to be the heaviness due to the gravitational pull on the mass. So sometimes, even if we have a very big something, maybe it has not as much weight. Like a pillow. If we think about a pillow, it has the same amount of matter as a rock, about that same size. So if we had a pillow and we had a rock, pretend those are the same size. So this is a pillow and this is a rock. Our pillow and our rock have the same amount of matter and the same amount of mass. However, we have different weights here. So this is going to be this matter and the mass equal the matter and the mass. They have the same size, they have the same amount of matter. But the pillow is going to have a far less weight than the rock does, while the rock has a lot of weight because this is the heaviness due to the gravitational pull on the mass. Now for chemistry, here's the basic definition. Chemistry studies the composition, properties, and interaction of matter. So here we start back at the top with our matter. And we're going to be talking, I know I've said the word chemistry and it brings that shiver to yourselves, but we're also talking mostly about biochemistry. So this is why it's really fun, because we get to talk about exactly how it has to deal with the body. Biological chemistry, because we're studying the physiological processes and disease. So we're trying to figure out how chemistry affects things in the body and exactly how those are going to maintain their ability to continue to work. So we've said a little bit about elements. An element is going to be the simplest type of matter with certain chemical properties. There are 92 naturally occurring elements. So there we go, up to, if we look at our periodic table, if you look at the element with the atomic number of 92, that's going to be the naturally occurring elements, everything that occurs naturally in Mother Nature from 92 or from 93 and above. Those are going to be some synthetically created elements, so not naturally occurring. They were made in a lab. But remember, from hydrogen up to iron are the only ones that can be created in the center of a star in those fusion reactions, because then iron is too heavy to be able to be fused with something else. So our elements, we said they're the simplest types of matter. So the matter, we said, is anything that takes up space and has mass. Matter is composed of elements. So matter is composed of elements. Elements are the simplest type of this matter. So when we look at the periodic table, we already said if we look at hydrogen, it's that square and it has the atomic number of 1. Then we can go to helium. Helium has 2. So if we look at this, we are talking about individual elements, the individual element of hydrogen and the individual element of helium. This is the simplest type of matter and has specific chemical properties. We already said that hydrogen only has 1 electron, while helium has 2 electrons. Those are going to be some of the certain chemical properties that we're going to discuss. And those certain chemical properties, as we already talked about, deal with whether or not they're going to react with other chemicals. So when we're looking at the periodic table, each of these boxes, each of these elements is talking about a single piece of one of the levels of organization. So if I said I have the element hydrogen, am I talking about subatomic particles of hydrogen? Am I talking about an atom, or am I talking about a molecule? I know we haven't gone over necessarily the definition again of a molecule, but we know a molecule is 2 or more atoms. So if hydrogen is this, a single atom, then I just gave you the answer. So hydrogen on the periodic table is going to be a single atom of the chemical. So we said hydrogen on the periodic table. The periodic table is going to be a single atom of a chemical, a single atom of an element. Which is a chemical. So every time we see this box, we know the box of hydrogen is talking about all of the properties that a single hydrogen atom has. This box of helium is talking about all of the properties that a single atom of helium has. Lithium, beryllium, etc., etc., all the way up to even our synthetic elements. Each box with information in it is telling us what those chemical properties of a single atom of those elements have. So that's why we need to be able to read the periodic table. I've also included another video of how to read the periodic table in there, which is, or in the links if you go and look, so that will be also very helpful. if this is confusing to you. So we're talking about those elements. So we said elements are going to be a single atom of an element. So we're talking a little bit about our levels of organization again, from smallest to largest. So for our elements, we're talking about an atom. So then we move up to compounds. Compounds are chemical combinations of different elements. So this says combinations. So can we think of, if we take a combination, so probably one or more atoms together. What's the definition of one or more atoms? Yep, that's going to be a molecule. So this is starting at a molecule. This can go up. A compound can be chemical combinations of different elements. So that means we can have a hydrogen and a helium making a molecule, because that is two atoms, two or more. And then a macromolecule is going to be two or more molecules. So it could be a macromolecule. A compound could be a macromolecule depending on how many atoms or how many molecules it has. So a compound, if we're talking about, let's say, carbon dioxide. We know we have a single carbon and two oxygens. So that's going to be a combination of different elements, and that specifically is a molecule, two or more atoms. We have two oxygen, more a carbon dioxide. A macromolecule we'll probably talk about a little bit later. So our compounds, chemical combinations of different elements. We said the elements on the periodic table talk about a single atom of that element, of that chemical. And here we give the definition of atoms again, our smallest particle of an element that have properties of that element. And that is where the periodic table is talking about it. Each block of the periodic table is telling us what that chemical and what it is and what properties it has. Specifically for our biochemistry, our biology that we're discussing, we're going to know that the body has different elements required in different amounts. We can think, yeah, duh, of course it does. We need more oxygen, then we want carbon, but we are also carbon-based life forms. So is that actually true? We want hydrogen because we know H2O is water, and our body is 70% made up of water. So we need a lot of hydrogen, we need a lot of oxygen. We are carbon-based life forms, so we need carbon. We can say we need nitrogen, phosphorus, calcium for our bones. All of these are chemicals that we are going to require. So the different amounts are going to be subsidized by our bulk elements, our trace elements, and our ultra trace elements. So required by the body in large amounts, we can see our top 6 elements are going to be carbon, oxygen, hydrogen, nitrogen, sulfur, and phosphorus. So some that you don't even think about that we need, but in large amounts does our body need. So here, it's interesting because we can think of some other ones that I already said. So like calcium is very important, but it's not part of our bulk elements. And like potassium is also important, but it's not in our bulk elements. That's just because of the size of the atom as well as where they exist. So we know that those are also very, very important, but not in the top 6. Then we get to our trace elements required in small amounts. Here we can see elements like iron and like iodine. Very important for us. We know iron is used in the body, and if you are anemic, you don't have enough iron, you need those to be able to use our hemoglobin. But they're still considered trace elements, depending on, again, how big the atom is and exactly how much we use it in the body. Then some chemicals might surprise you, because here we have ultra trace elements, obviously telling you that they are very, 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 very minute amounts. Does anybody know what this chemical is? AS. This is actually going to be arsenic. Can we think of what arsenic is used for? Yeah, poison. Arsenic in large amounts is used for poison, especially if it's not treated properly. However, our body actually requires So this says it's required by the body in very minute amounts. So yes, maybe the discovery of arsenic poisoning was actually because we decided or discovered that arsenic was actually a requirement of the body and was trying to figure out what trace amounts the body needed. That's highly unlikely, but we did discover that arsenic is actually needed in the body. But if we have too much of something, it could be very bad for us, just like too much arsenic leads to death. So let's try not to do that. We want to keep that in the ultra trace element category. Okay, I know we're going to go over similar things over and over and over again, but that also makes them very important. It reminds you that you really need to know these definitions in order to move forward. So some of the particles we said are matter. Our matter is the amount of matter, the amount of stuff that something has, and our mass is the amount of matter that is present. So we said our smallest level of organization is going to be our subatomic particles, which include our proton, electron, and our neutron. If we put all three of those together, we are going to build our atom here. And our atom is the smallest particle of an element that has properties of that element. We said that the periodic table, so if I drew this block and put hydrogen in it, I know that from the periodic table, that hydrogen box is talking about a single atom with however many protons, neutrons, and electrons it has. Luckily for us, we know that the atomic number is 1, so it has 1 electron. And it is also going to have, are we talking about that yet? Yeah, in just a moment. Talk about that in just a moment. So the amount of electrons also determines how many neutrons and protons it has. So the atom is the smallest particle. Making that up, we have the electron, the neutron, and the proton. And we already said that the electron has a negative charge. The proton has a positive charge, and the neutron has a neutral charge. So the electron is an extremely small particle within the atom. It has almost no weight and carries that negative electrical charge. It's in constant motion around the atomic nucleus. So here I want you to remember this. An electron has an extremely small particle and has almost no weight. So when we're talking about the weight of an atom, we are mostly talking about the proton and the neutron. We are never going to get the weight of the electron added into the atom's atomic weight, because the electron is basically negligible in size. While it does have a negative charge and is very important for the reactivity of that atom, it is not going to be important for the weight of the atom. So then going into our protons are a relatively large particle within an atom carrying a positive electrical charge and is found within the atomic nucleus. So I know on this atom I've been drawing as a little small circle in the middle, but whenever we look at an atom, I'll draw it a little bit bigger, the nucleus is going to have protons and neutrons, and then we will have the electrons circling around the outside in what we call an electron shell. So if I had 1 electron, 1 proton, and 1 neutron, this is going to be our hydrogen atom. But then if we go to the next level up to our helium, we know this has an atomic number of 2. So we are going to have 2 protons, 2 neutrons, and then 2 electrons out here. And then as we go up, lithium, beryllium, etc., those are all going to grow because we want our elements on the periodic table to be electrically neutral. Now, electrically neutral means they have no charge. So the number of neutrons really doesn't matter because they have no charge. So what does that mean for our other subatomic particles, our electrons and our protons? It means that we need to have the same amount. because if we have one positive and one negative, they're going to cancel each other out, right? We have two positive and two negative, those are going to cancel each other out, which then just leaves us with our neutrons, leaving us electrically neutral. So we really want to maintain that in our elements. So no matter how many neutrons we have, as long as we have the same electrons and protons, we are going to have an electrically neutral atom. So as I said, electrons, relatively small particle, almost no weight. Protons, relatively large particle. Neutrons, relatively large particle. So that's why those make up the atomic nucleus. We said the neutron has the same weight as a proton, uncharged and thus electrically neutral, found within the atomic nucleus. But still, we need the same number of protons and electrons in order to remain electrically neutral. If we do not have an electrically neutral atom, it's going to make something called an ion. An ion is going to be a particle formed from an atom that is electrically charged because it has either gained or lost one or more electrons. So let's say that this hydrogen atom gains an electron from another atom. This atom now has one proton, one neutron, and two electrons. So this hydrogen atom is no longer electrically neutral. It is actually going to have a negative charge. So this is now an ion because it is negatively charged. So it is electrically charged because it has gained or lost. It has gained an electron, meaning it has two negative charges over one positive, making it even more negative. If it loses that electron that it had before, it is now back to electrically neutral. So this is back to our original hydrogen atom. And how this works is also going to dictate how the rest of our chemicals react with each other, whether or not they gain or lose electrons, because as we said before, those electrons are what are in play, are what are going to react with each other based on the electronegativity of that atom. So an ion is a charged particle, gained or lost electrons, changing the electrical neutrality of the atom. And then we already know a molecule is one step above an atom. So an atom is going to be the smallest, while a molecule is two or more atoms, like our water molecule. We have two hydrogens or more, making three atoms, two hydrogens and one oxygen. So we have three atoms, making it a molecule. And we said about our major elements, our bulk elements, and our trace elements in the body. We looked at the biggest percentage in the body. So our top four are what are most important to remember. Oxygen, carbon, hydrogen, and nitrogen are going to be our top four. If you don't need to remember them in order, a good mnemonic to remember them is CHON. That's going to tell you the top four major elements in the body. However, this is going to be talking percentage-wise by weight. I just started talking about our compounds and our molecules and how we have a lot of oxygen in the body, but it is going to be delivered and to be connected by a lot of other things. So we talked about the beginning of the world and how hydrogen is used in fusion reactions and then was released. And it's what helps to create you, because you're made of stardust. So if we look at those hydrogen atoms, this only makes up 9.5% of our human body. What did we say makes up about 70% of our body? Water. So water makes up a good majority of our body, 60 to 70%. And what is the chemical formula for water? H2O. So if we have about 70% water, and the chemical formula for water has 2 hydrogens and only 1 oxygen, each molecule of water has literally double the amount of hydrogens, than there is oxygen. So then why is hydrogen only 9.5% when we know water makes up about 70% of our body? If we can think about what we know about the atoms of each of these individual elements, that will give us a little bit of forward thinking. So one more time. If we have a human organism made up of 60 to 70% water, and the chemical formula of water has 2 hydrogens and only 1 oxygen, then why, with our body being made of double the amount of hydrogens, does the percentage of hydrogens only make up 9.5% of the major elements in the body by weight? This is going to be our kicker. We said by weight, and if we remember, the definition of weight is the amount of gravitational pull on the mass of that element. And if we also remember, we said that oxygen has an atomic number of 8. So that means we are going to have 8 protons, 8 neutrons, and then 8 electrons, 2 in the inner shell and 6 in the outer shell. And then so that's our oxygen, and then our hydrogen, we know, is the atomic number 1. So it's going to have a much smaller, it has 1 proton, 1 neutron, and 1 electron. So if we say by weight, it's the amount of gravitational pull. Wouldn't oxygen have a higher gravitational pull because it is a larger atom than hydrogen does? Yes. So even though our water molecule has double, like I said, double the amount of hydrogens than oxygens, this is only going to give our body 9.5% because it is talking about by weight. We have smaller hydrogen atoms than we do oxygen atoms, and those are really what is going to make a difference for the major trace elements in the body. And we can think of this all the way down, nitrogen, calcium, phosphorus, potassium, sulfur, all the way down we can think of this, because even though we might need a whole lot of calcium in the body for our bones, it might be a smaller atom than any of these above. And that's why we have only 1.5% of the body being calcium by weight. So we've already talked about this a little bit, and as I said, if we repeat it multiple times, that means it is extremely, extremely important. So here we're talking about our atomic structure being an atom, where it says, literally right there, an atom. So an atom being composed of subatomic particles, we know we have protons, neutrons, and electrons. Our protons being large particles, neutrons large particles, and electrons small, not talking about their weight. Protons having a positive charge, neutrons neutral charge, and our electrons having a negative charge. So we already said that atoms have a central nucleus with protons and neutrons there, which is why the nucleus acting a little bit like the Earth, while the electron is a little bit like the moon. The Earth is much, much bigger, having gravitational pull, having mass, having weight, while the moon, or the electron, is just kind of swinging around outside of it. While it has the gravity of being pulled by the nucleus, it does not have enough weight to move about on its own. So here we're talking about our electrical neutrality again, because the number of protons has to equal the number of electrons in an atom. The neutrons do not have any electrical charge, which is why we only talk about them when we're talking about weight, since they are large particles. For our electronegativity or for our electrical charge, we need to have the same number of electrons and protons. So let's look at our atomic structure here. We can count one, two, three electrons. So we have 3 electrons. We have 1, 2, 3 3 protons. Protons, and we have 1, 2, 3, 4. Interesting. 4 neutrons. So our 3 electrons give us an electrical charge of 3. 3 protons, electrical charge of 3. So these are going to cancel each other out. Does this make it electrically neutral? Yes, this is electrically neutral. And this, if we look at the number 3, we have 3 electrons, 3 protons, making this electrically neutral, making this a element of the periodic table. And if we look at what has the atomic number of 3, that is going to be lithium here. And our lithium, as we said, is electrically neutral, same number of protons and electrons. So why, with this atom being electrically neutral, 3 electrons, 3 protons, why does it have 4 neutrons? Doesn't that change anything? Does that change the structure of the atom? Does that make it a different chemical? No, because the chemical is going to be defined by different things. So here we're talking about the atomic number. Our atomic number is going to define the chemical, because if I say an atomic number of 1, we're talking about helium. If I say an atomic number of 3, we're talking about lithium. If I say 8, we are talking about oxygen. So what is the atomic number defined by? This is the number of protons in the nucleus of an atom, of a specific element. So the atomic number is defined by the number of protons. As I said, if we have the same number of protons, if they equal the number of electrons, then we have an electrically neutral element. We have an electrically neutral atom. But the neutrons can change their number without changing the chemical. So here we said the atomic number is the number of protons in the nucleus. So if we look up here, this has 1, 2, 3 protons, making the atomic number 3, making this lithium. So if we added another proton, the proton, if we wanted it to be electrically neutral, we would have had to add another electron. So we now have 4 electrons, 4 protons, and 4 neutrons. So this would now have the atomic number, because the atomic number is the number of protons. So the number of protons would have an would have the atomic number of 4. And what would that be? That would be beryllium. So we're going up. Now we can take that all back, and we're still left with lithium, but it has a different number of neutrons again. So why do 4 neutrons not change the atomic number? Because it's the number of protons. So then we get into the mass, because we know the mass of the atom deals with the number of protons and the number of neutrons, because those are on the atomic nucleus, those are large particles, and they have mass. So the mass number is the number of protons plus the number of neutrons in one atom. The electrons don't contribute to the mass because they're so light. We said that. So if we talk about the atomic number and the mass number of lithium as a normal element. It probably has 3 electrons, 3 protons, and 3 neutrons of a normal element. And this is going to have an atomic number and a mass number that are going to be equal to the electrically neutral element. But as we said, we have changed the number of neutrons here, which are then going to change the mass number because the number of protons plus the number of neutrons is now different for this lithium atom, which then gives us an isotope. So the word isotope is defined by the same atomic number but different mass numbers. So as we said, if we have a lithium atom and we have three protons, 3 neutrons, and then 3 electrons. These are all going to have the atomic number, because the atomic number is defined by the number of protons. This has the atomic number 3. And our mass number is the protons plus the neutrons. So the mass number, it's going to be different because the protons and the neutrons have a different weight, but we'll just say it's 6. So if this is the normal number for a lithium atom, once we add that extra neutron, this is now going to change the mass number to 7 because we have 3 protons, 3 electrons, but 4 neutrons. So we have the same atomic number, but we have a different mass number, which gives us an isotope. Same atomic number, different mass number. So if we change the number of neutrons, we get an isotope. What would happen if we changed the number of protons? So let's say instead of an extra neutron, we still have, so right now we have 3 protons, 3 electrons, and 3 neutrons. So instead of changing the number of neutrons, what if I change the number of protons? So we're not adding another neutron, we're adding another proton. What does this change? Does this change the mass number? Yes, because the mass number is protons plus neutrons. But does this also change the atomic number? Yes, because the atomic number is defined by the number of protons. So now we don't only have something that has a different mass number, but it also has a different atomic number, making the atomic number, see if I can write things, the atomic number is now 4, which makes this not lithium, this is now beryllium. So changing the atomic number changes the chemical entirely, but changing the mass number just makes it an isotope. Same atomic number, different mass numbers. Our isotopes contain different numbers of neutrons, but the same number of protons and electrons. The same number of protons and electrons gives us what? You're right, electrical neutrality. Neat. So our electrical neutrality means that we don't have a charge. It means it is not an ion, so it doesn't have a positive charge or a negative charge because the positive protons and the negative electrons cancel each other out. We have, when we change the number of neutrons, however, we get an isotope, and for any element, the atomic weight is often considered the average of the mass numbers for all of its isotopes. So some of our chemicals, some of our elements, like oxygen, forms isotopes with other numbers. So if we were talking about oxygen here. Let's say oxygen, we know has an atomic number of 8. So I'm not drawing all of them individually, but let's say there are 8. So we have 8 protons, 8 neutrons, and 8 electrons. This is an electrically neutral atom of oxygen. So our atomic number is 8, while our mass number is 16. We can change the number of neutrons here by adding or subtracting them. So some oxygen can change. We can have oxygen 16 here in the middle, oxygen 16, but we can also have oxygen 15, or we can have oxygen 17, or oxygen 18. This is going to change the atomic weight. This is going to change the mass number. And so when we look at the atomic weight, this is often considered the average. So that would be if we took all of these, if there were only 4 isotopes for the chemical oxygen, and we added them all together, and divide by 4, because there are 4 of them. That would give us our atomic weight of oxygen itself. Those are isotopes. So here's another clinical application. If you guys want to go back and read that, you can. And then we get to molecules and compounds. So like we talked about in our levels of organization, going from smallest to largest, we just spent a whole hour talking about atoms and how important they are. And now we will finally get up to our 2 or more atoms to make molecules, and how compounds are similar to molecules but are not exactly that. So I'll see you when you come back.